I guess that should have worked. Okay. Wait, from what I understood, like you essentially want a lot of temporal coherence between frames, and you won't do that by directly generating an image. You essentially try to generate all of these lower dimensional motion maps somehow, and uh, and then you and then you somehow do a rendering process to uh, actually generate videos from it. So I guess that's an interesting way of looking at problem. I know like there are a lot of methods that do something similar to motion priors. Uh, like at one of the earlier discussions, one of us volunteered to talk about MOFA video, which also tried to like get the motion prior somehow, and then did it. And then there is like, of course, text to video zero and those kind of methods. And what they do is, uh, I however think that this is really different because what they do is you get like some motion prior, which is probably in this image, and then you solve a flow matching problem. And with that flow matching problem, you probably end up with, uh, I guess, like the way I understand it is, you end up with, if there was something over here, you end up with a warped version of this, and then you add noise to this, and then the generation process uh, probably like denoises this noise and happens to actually go from warping to a pretty clear image. So I guess that's how most of the popular methods used to work, uh, and they do something really different, uh, which is generate like dense motion fields and directly render videos from it. There's no generation process happening after getting these dense motion maps. Uh, yeah, they seem to like start the introduction of the paper with like some commentary uh, on how the natural world is always in motion, which I guess is interesting. Uh, and As it seems like from the first paragraph to me, like they only talk about all of these subtle oscillations and trying to like model rhythms, so to say. So uh, yeah, that seems interesting. Maybe like we can take a look at the method. Uh, so so they start by giving an overview of like what their notation is, and I guess like most of this is pretty standard, so we can skip by all of this notation stuff, and go on to like how they try to do all of these motion representations. I maybe like the way I would go about this, at least like when I first read it, is just go through the figures. So yeah, I guess I'll just try to do that here as well. So they say we visualize the average power spectrum. Okay, so apparently, according to them, if you do have if you do have natural oscillation motion videos, uh, which is also really hard to get, but they do have some natural videos which don't have like anything going on. Then if you try to see then if you try to see the frequency of the motion, it seems really small, and and all of this is like so essentially I think like the main point of this figure is that all of the motion frequencies should be really small. You shouldn't end up with like super high frequencies, and that kind of stuff, which you don't want for all of these still looking videos, or like idle motion videos. Uh, so so that seems, I guess, kind of expected. You would expect like objects in nature to like have a lower frequency of motion. and then they have their main methods figure. So maybe it's like some use to go through this and see like what they do. So they start with uh, so all of this is like a latent diffusion model. You are starting with a latent. So I guess like the uh, there's like so probably you have like a lot of videos, then you convert it into x cross 4 tensors, and then you noise it and get these latents. So yeah, there probably should be an image that goes into the encoder here, but never mind. Uh, then you get like all of these noisy latents, and then they use diffusion for something. So they introduce this. I guess they actually don't introduce this thing called spectral volume, which they use a lot. Uh, it's actually pretty popular in the field, and I know that like all of these uh, text to video models often don't use this, which is why I guess this is interesting. But there have been a lot of surface renderers in the past, and uh, all of these uh, all of these other kinds of graphics methods that have used spectral volumes quite a lot. Uh, and I guess like one of the from what I understand, like one of the main things with spectral volume is that you essentially want to try and model you essentially want to like given a series of images, try and model or try and model the motion somehow, and you end up doing it with uh, doing a temporal Fourier transform on it. But it's very hard to predict individual frames of this in an autoregressive manner. It's you cannot like take the previous two frames and predict the next frame from what I understand. um, because you just like end up messing up the temporal coherence. So probably like any autoregressive method for this uh, would be really hard to make work. Now I know like there are uh, there, there are I guess like there are two sets of methods that do it in this autoregressive kind of style, which is what you do is you first take like a model and then you predict the motion for the end frame or like a middle frame, and then you solve an interpolation problem over here. Uh,
It's also coding the video. You don't just do it manually, but you do it poorly.
y- yes, um, I you could say, well, it would, but you'd also need like, I guess like you'd also need if you want to like do it that way, you would also need like the V parameterization, which has been really popular, and probably you would also need like and then there was like a fix to so the way VDM works, right? The original VDM paper, the way it works is that they try to do a very similar problem to what you mentioned, using like maybe it's easier to write down what you should.
I would the video diffusion paper. It uses a video transformer instead of um, like a vision transformer breaking things up into little patches. Does this more of it as well? Is that all it is?
Uh, Pretty much, but then they also introduce like this thing called so the problem with like any motion trajectory that you have is uh, oh, uh, sorry, there's like something on the screen. Wait, but like a problem with any of these motion trajectories that you have and that the VDM and other works after that do is that I guess like if you try to write down you want to solve like the ZT given ZS problem, and then if you try to write down the update rule in DDIM, you essentially want like I guess like visually what you want is this could be your X, and then you could have Z, Z here, uh, and then you have a VT direction over here, right? And and this is the vector that you're moving geometrically in the DDIM update rule. This would be the phi that you use for the Piesner calculation, and you essentially want to move this in like the minus VT direction, right? Just in like standard diffusion model notation. So, so this becomes really hard to compute, and so what they also do is like introduce a V parameterization along the lines of epsilon parameterization, like they did for the original diffusion models. Uh, so you can just like, oh yeah. So I believe like the final result for this was, so essentially it's a bit of trigonometry and it's a very interesting proof. But I believe like the final result they get was something along the lines of you get like uh, alpha t. Uh, yeah, I probably can't remember the final result. It's but it's essentially like an interesting proof, and the proof sketch, the original proof sketch is you start out from this geometric intuition, then you plainly just use trigonometry on this, and it all and finally you can just use the trigonometric identity, and it boils down to a very simple expression. Yeah, it's a pretty easy proof from this geometric intuition.
So it's not just like separate.
Yeah.
It's more expensive.
Yeah, and this makes a lot of the color shift problems and temporal coherency problems go away. So that's what VDM shows, and uh, then they also had this fixed conditioning. So there was a problem with like so essentially what the problem was becoming is when you try to predict like volumes, you are no longer predicting images, but you're like trying to predict like some of these video volumes, right? Yeah, this would be like a patch of the video across the whole thing. So essentially, if you try to make any one of the axes of these really long, uh, as it turns out, with all of these diffusion models, you end up just you end up just making a oversaturated image, and it all looks ends up looking quite similar if you just use the traditional diffusion way of like predicting these volumes.
So
Oh, oh no, it will all like most of after the denoising process, probably like after DDIM or DDPM, most of the pixels would end up being very, very close to the mean.
oh, so it's
Yeah. So this was another problem, and then there's also an interesting way to write there's also an interesting way to write the guidance for this. So you can change you can change the way the generation for this is guided, and that was also another thing that the VDM paper did. And both of these like have been quite popular, but essentially like they allow you to get around most of the color shift problems, and temporal coherency is still a big problem even with like these methods. Uh, so I guess like that's what all of these earlier approaches did, and it would be like very hard to just represent an image to the temporal domain uh, to model it. I mean, probably like Sora and all of those do the same, but in general, I guess it's a really hard problem.
or maybe we look into this more. Like just have so much.
Yeah, I guess so. Uh, this is actually like particularly cheap if you can do this on like if you actually like do this motion stuff on meshes. and like discretize it somehow, it's particularly cheap to do this, to run inference. Uh, and training is also reasonably cheaper than all of these video models. Uh,
Just a quick announcement. We got the shawarmas now. Please read video of things. Could you change your screen share? Like,
oh, sorry, what should I do?
can you share the one?
Oh, okay. Well, let me just try like, here we are trying to like do this YouTube live stream thing, and it always has some or other problems. Uh, yeah, so I guess like the way they approach this problem is so 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 you do, so what they do is so all of these latents what they represent is Fourier coefficients of your motion of your motion. So you probably have like all of these so you do have like all of these latents, and they all of them across a given axis have like an x and y, like the standard Fourier coefficients. And then you then your problem is just that the diffusion model is predicting these Fourier coefficients. So this iterative denoising problem, this entire thing, well, not the decoder, of course, but this entire thing, this is all working on these Fourier features. Um, so this is the part where they start using a spectral volume. So what you do is the entire training process, uh, the way how it works from this figure is maybe like let's talk about training first and then in inference. So in like training, what you end up doing is you take a bunch of videos, you you essentially first try to get like some ground truth motion maps for all of these videos. And I guess it's very important for these motion maps to be super dense, so you get those for all the videos. And then during training, what you actually do is you make like this spectral volume, and all that does is like a bunch of Fourier coefficients for how a discrete version of the image moves through time. So now you can represent that through essentially like a spectral volume. Now that you have that, you solve the standard latent diffusion model problem. uh, so yeah, this is like just the standard latent diffusion model problem. And now after the decoder, you again end up with like a spectral volume, right? So now from the spectral volume to do some kind of rendering. So I guess we could come to that. But before that, this so 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 this is a standard latent diffusion model problem, but they kind of slightly modify it. All of this stuff in red over here. Uh, so they kind of slightly modify this. Uh, if this doesn't look so familiar, um, it's actually very familiar. It's a very popular technique. They just put it differently. If this doesn't look familiar, think of it as all of these. So when you try to like take a text to image model and try to inflate it to text to video, what you end up doing is, well, you of course like average weights across channels, but probably you also change your attention layers uh, to to take like most likely you would do something like take like queries and keys from other frames, or take a part of queries and keys from other frames, and take the values from the same frame that you're working on. So this is essentially just that, but uh, in the frequency domain, and they do it on all of these spatial volumes. So it's essentially just that. Uh, and you might like remember this from stuff like text to video zero, and There was also control net video. Those approaches, they do in some way, in they are pretty equivalent to this. It's like the same way of representing it, uh, even though they write it like quite differently. Uh, but so essentially, you do that in the. So I don't know why this is here, but anyways, this should be over here. So this is a change in the model itself, and yeah, it's actually like really easy to do this because all of this is just a DIT. So uh, yeah, you can like just do this for every single attention layer or like a few of the attention layers. And oh, by the way, this doesn't require you to like retrain anything, right? You can, I mean, they do this when they are training, but uh, ideally you can like get away without training in this fashion and still use weights uh, weights from like standard DIT and reasonably enough approximate this because uh, yeah, it would just be like pretty similar. It's just this minor difference that's making things a bit better. So I guess like so you have the latents after the decoder, you get spectral volume, and so 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 now you have like all of these spectral volumes and like Fourier coefficients, and you can easily make that into a dense motion map. So I guess this is not the best way to represent this. They had an example earlier on figure one, which I saw, which is a better, I guess, like a better way to represent this. Yeah, so you have like all of these for uh, all of these Fourier coefficients for different frequencies, of course. And then what you can do is just uh, just use these, and what these actually represent is the motion. So then you can render those kind of values into what they write over here into like these motion maps. Well, this is still spectral, but you then render it into like all of these motion maps. So that's essentially like how their entire problem looks like, as it seems from like this figure. And oh yeah, so I don't know where it is, but we can get to that section. They essentially have a separate section on rendering, which I saw in there. Uh, it's not so straight. So you can get from maps to like motion maps. I guess like some people have done it in the past, but it's not very popular in the community. So they talk a bit about rendering as well and how this rendering happens. So I guess like that's the next section over here. So uh yeah, they now want to like given a spectral volume, you have like some spectral volume, and then you want to render a future frame. Uh Essentially you don't want to use any machine learning over here. Hopefully enough, it will be at good enough frequencies that you don't need any interpolation and all of that crazy stuff. So uh yeah, all of this essentially should be just traditional computing, no learning algorithms here. Ideally that's what I would think. Wait, yeah, essentially like so they first start by getting like a dense motion texture, and that's very straightforward, right? You can just do an inverse Fourier transform. So that seems pretty standard. uh, and then they refer to figure 4 for like what you do after the inverse Fourier transform. So maybe like let's take a look at this. Yeah, so this also looks very similar, a standard splatting problem. So uh, what you do is now that you have got all the dense motion maps at different frequencies, uh, you quite literally just splat them into into single motion maps.
So your entire process is the Fourier domain, or are you shooting the first FFT with that complicated? It's just generating motion.
It's just
I understand you're not learning the rendering process, but I think you're getting just some information from it.
no. So in the backprop, you don't need to do inverse FFT at all.
Oh.
All of the diffusion process is just on the Fourier domain. You'll have
Surprise.
no, because you still have conditioning from images, so
Oh,
kind of works.
Sure.
Yeah. So uh yeah, you still have like this I0, which it's supervisor conditioned by. So
oh, yeah, okay.
yeah. And so now you just do this plotting problem, and I would assume like you would need to do some smoothing, but uh, do they smooth stuff? Apparently they don't, from like reading the caption. So I guess there's no smoothing involved, uh, which is I guess a bit surprising. Uh, but yeah, then they say that they yeah, this essentially gives you like outputs similar to a flow matching, gives you like all of these warped features, and then you can pass it to an image synthesis network, which would be very standard, just like take all of these individual plots and render a full image. Uh, yeah. So so I guess like the rendering process is uh, pretty standard. They do say that they need to, or at least they do fill in missing content and refine the warped input. Oh, so I guess like this defining part is they don't show it in like the figure, but this defining part is where all of that probably smoothing or like frequency filtering could happen. Uh, and what I think is like particularly interesting is like they need to like fill in missing content, uh, w- which I wouldn't have expected to be the case because I would have assumed that when the network is producing all of these Fourier features, it's doing it reasonably well for the entire image. There isn't like a part of the image where those features look really bad. That's what I would have expected. But they say that it is actually the case, and they need to like, uh, and their synthesis network also like does all this filling in. So I guess that's an interesting part of it. uh, when I was actually playing with the demo, I actually thought that the filling in wasn't good enough. Because so there's actually one of these demos they had, and I was trying it out myself. And essentially, if you go to this demo, and you already see like all of these artifacts from uh, problems in the right, and so it isn't just when I'm doing the dragging, which is where of course the model isn't run, but even after I do the drag uh, and leave it, there's like still a few artifacts on the rightmost part of it if you look closely or try it out yourself. So probably like there's some problems with this filling in still.
Can you explain like how splatting works? Like I'm completely like new to it, like I've never heard it.
Oh yeah. So uh yeah, not to I guess like if you haven't heard about it, not to be confused with 3DGS, which is super popular, and it's also called Gaussian splatting.
Like the generating all that.
Yeah, yeah. It, it it solves like a similar problem to nerf, but and that's like super popular out there. and it's and this is called splatting, but you don't do Gaussian splatting. Uh, so I guess like that's a way to start out. Uh, but yeah, essentially like the splatting problem is actually very easy. So um, it's just a big name given to like a simple problem. But essentially, what you do is you have like this feature extractor. You already trained this. Um, you can run it. So now you will have like all of these. So now you'll have all of these, and then you also do, let's say, inverse FFT. So now we have all of these motion texture maps or uh, motion textures. You essentially just like take all of these motion textures and put them on top of each other, the frequencies which you need, and that's pretty much what uh, splatting does, like the knife splatting does. So yeah, probably if you're thinking about images, uh, images, and after doing inverse FFT, the way you can think about it is, let's say this is you get two images, right? So this is phase, and then this is like your actual FFT, uh, or like so, and let's say this is like phase. Uh, so what you do is you find out a frequency from this which doesn't work, or that you decide. Let's say that I'm only taking like this part of it. Uh, so then I like take all the so then I do like all the Fourier transform. So I can then do like all the inverse FFT stuff, like all the multiplications, additions, and just superimpose stuff on top of it. That's how you build an actual image, right? You're just doing that for motion maps.
So where do the features come into play then? Like, why do we need a feature expand?
Oh, yes. So if you remember, like from what I understand, like the features are coming from figure two, right? Oh, sorry, figure three. So the features is coming from like this neural network. So this neural network will give you features at like different frequencies of motion. Uh, so you essentially end up with like uh, you essentially end up with like all of these different frequencies that you need to sample from the neural network. So so yeah, that's why you have like this feature. So this feature extractor network does exactly that. It allows you to like get all these FFT values or Fourier values. So yeah, they do all of this rendering, and uh, and they have formalized it over here. But I think like most of this is pretty standard stuff. It's nothing novel, and people have done this for a while. So we can like I guess skip past all of this formalization. Uh, w-
What artifacts saw before? Right. Do you think that's just an innocent problem? So you can save by increasing frame rate
mm,
problem, or do you think it's more than that? Because to me, just the magnitude of the drag factor, nothing is serious, but it should have some influence.
so my thought on that is, or on that is that I guess like two things. One is so if you actually see like the data set that they have, they by the way collect like this new data set, uh, which is an interesting collection because I don't know where they talk about it. But anyways, they collect this new data set, and it's an interesting data set because like all the video data sets have something happening in them, and this doesn't have something happening in it. So I guess like that's an interesting thing. But but I guess like one of the problems of like collecting a data set with something not happening in it is you just end up with like a very particular class of data. So I'm very sure that what we tried to do, like the very big drag, is most likely OOD for this problem. Anyways, uh, there wasn't something like that in some similar to those big variations in the data set at all, probably. So one is, I guess, like most certainly a data problem, and then the other, I guess, is like I do think it's not just an aliasing problem. Yeah, you probably need like better ways to represent these somehow. Uh, yeah, I do think it's like more than just aliasing. Yeah, probably that would be an easy fix for it, is you like account for aliasing or do some kind of interpolation. But yeah, I guess like to solve this, you would need like a lot more. So that's pretty much their method. Uh, and yeah, they talk a bit about implementation details, but I guess like that's yeah, probably like there's no need to like go through implementation details. Uh, they talk about a few applications. And the first is, of course, like image to video, uh, which is quite standard because that's exactly what like all of the figures show, image to video. Then they also try to, I guess, like let's come to this later because the second one, because interactive dynamics is a very similar problem to image to video. So, so the demo they showed was actually interactive dynamics, because you have some trajectory across which you will condition it, and it needs to go through. So, so essentially, they do this in a in a standard way. So it's pretty similar to like all of these methods that modify text to image models for these kind of trajectory based problems, or like editing problem, or very niche kind of editing problems. So they use something very similar to this. And there's this thing called modal analysis, which is super popular for these kind of methods. Uh, but essentially, like all that you do is you solve like you take a bit of inspiration from physics and like try to solve, as they like very aptly describe over here succinctly, uh, like try to solve this mass spring system. Uh, so so and this for the most part is very cheap to do. There's no It's just like traditional algorithms, and you can do it very easily. You don't need to retrain the network at all. Uh, so you can do this very easily without like retraining, that is. And then they also talk about seamless looping, which I think is a very hard problem to solve. Uh, People have done it somehow, but it's quite hard to solve this very properly. So yeah, so for seamless looping, they do a bit different stuff when they are when they are doing inferencing, and when they are so what they essentially end up doing is you take the SDS, and and you already have like these three guidance vectors, right? So you have like so so oh, well, over here there's no text, but you can like just do standard classifier free guidance where you already have like uh, those where you already have those guidance vectors. And what they do is they also like do this part where they enforce each pixel position and velocity at the start and end frames. So yeah, essentially you can just like try. So essentially, what they just do is just modify standard classifier free guidance, and include this guidance where you want to clearly uh, have the start and end frames follow some same positions and same velocities at that point in time. Uh, and then you end up with start and end frames actually being similar. Yeah, so I guess this is an um interesting way of doing that. It's not I guess like the best way of doing it, or what I would expect to is uh maybe like this could be a inherent capability of it. You don't need to do this. It can somehow learn to do this for rhythmic motions and uh because like all the motions they generate are rhythmic motions, right? So I would assume that it would be really cool if they could have this be a inherent capability of this without like doing all this changes to classifier free guidance. So I guess, so that I guess would be like super interesting. Uh, but yeah, and then they talk about some experiments. So they also have a few baselines. These are popular models. Uh, then they have like so I guess like they have a ton of qualitative results, which is just a user study. So we can skip right past that. But uh, yeah, they have some useful stuff as well for results. They have some quantitative results, um, and essentially like what they're measuring is not the best quantitative measure, but they seem to do really well. They measure like FID and DTFED apparently, which under the hood are just like measuring similarity across frames. If you try to really, if you try to like oversimplify it, it's somehow trying to just like get similarities within frames. So I guess like but they also do see like very interesting results on all of these image and video synthesis problems. So that's very interesting. Uh, yeah, and they also seem to show that this works significantly better than all the previous approaches. So so that's quite interesting too. Uh, yeah, so that's pretty much all that they do, and they have this website with a few results, and maybe it's like interesting to go through these. And so uh, yeah, I think like there are some problems in this. It's not particularly complete, so to say. So and well, these are like very great outputs. It's almost impossible to say that these were generated and not captured by a video, at least for me. But there are like some problems if you especially like see this video, uh well, video or animation, whatever we should call it, animation, I guess. But yeah, well, if you like try to see this, there's there's very little part of this which is actually moving. And if you actually try to, I don't know how much you can see over here, but if you actually try to see it on your own machine at a better resolution, you can probably see that uh, there are some parts of this which are incorrectly moving as well. So there's like some part of the tree which is incorrectly moving with the chimes, just because there's like all of this space between the chimes, and that's where the tree is supposed to be, but it ends up moving inconsistently with the chimes. Uh, so I guess like this is a problem you can just solve by increasing resolution, but uh, yeah, this is an interesting problem. And then some of their other problems are also, at least from what I observed, is that if you see like stuff like this, for example, um, all of their well, we do want it to be idle motion, but all of their motion is quite limited to single objects or like single stuff. And this is also like quite visible in the demo. It's probably like not good enough to consider the demo because like this demo is on a mesh. Yeah, they say that this is on mesh warping, so it's probably like not good enough to compare demo and only see the results. But even in this, like, uh, it's not that you have all of the objects in certain motion, even when the uh, trajectory requires that. So, which would happen like, so the sunflower would be rendered nearly flawlessly, but if you have something else like this, where a lot of things are in focus and a lot of things should be moving, um, there's like not always all of them end up moving. So particularly over here also, if you try to move like a part of the tree, you would end up seeing that very particular portions of it actually move. So I guess that's an interesting limitation too from the results.
Yeah. Question. One, overflow signals faster and more. It's not a big thing. That's- Of course, it's the same. I'm sure details about how to make it faster. I guess two, how does it account for changes? Or scroll back up and go to their one. Let's see that this is just down. Down.
Oh, down. Sorry, up.
Down.
Oh, down. Okay. Oh, this one.
See that, yeah.
Uh, that's interesting. It's like not something that comes to mind to solve similar problems right off the bat. Uh, yeah, I don't know if it's like possible to do it in just with like the Fourier domain representations. Seems like a hard problem to solve, at least with this construction of it.
I guess. Way to do it, but just. A separate flow for illumination, you can combine the two together. But again, if they're already having data set issues.
Yeah, yeah, makes sense. Oh, and sorry, the first thing was how does it work faster?
Yeah, why is it faster?
Oh, it's so. Oh, so I guess like what I meant when I was trying to say that this would be faster, and is that and the way they portray this claim is that if you try to do if the if you try to do text to image as an or text to video as an end-to-end problem, or image to video as an end-to-end problem, instead of doing this compositional stuff, so to say, uh, that requires a lot more pre-training and a lot more world priors, uh,
Right.
which is why uh, training this is arguably faster to do, a lot faster to do. Yeah.
Well, it's not, it's just,
So
I think it's not, it's.
oh, at inference time, it's just like a standard
Yeah.
uh, DDIM
I wasn't
denoising
sure
process.
if it's something that's.
Yeah.
So I wasn't sure if they're touching it ways to do it with masks and ways so that. On the white background on some of the flows, they don't need to diffuse on every night, not all. There's some other way to do it. But I guess they just treat it like they would treat a regular.
Uh, yeah. So from what I understand, like they don't uh yeah, they don't try like any of those kinds of approaches. It's just that uh they probably ended up using DIT because it is the best thing to model any kinds of latents at all. Yeah, and probably like nothing Nothing that makes special use of like the masking or like patches of it. Yeah. So I guess that's all for today.